on what we have been doing here, use ACCESS-NRI for the post-SIMIP6 development. We have done quite a few things. The most recent work is the so-called perturbated parameter ensemble experiments. Share my slides here.
Does it work, or are you trying to share?
I try to share now and say if it works fine. You guys say anything?
Yeah, that's good.
Okay. All right. Okay. Yep. Before this most recent work, we have done the kind of ocean, the GM scheme tuning. There are two parameters we play with, and we done that. I think it's 8 experiments. We choose one from them, which is we call CJ888G. That one we think is pretty good compared to the control ones in terms of the ocean behavior. But anyway, so there is one thing is not that good. Actually, is the ENSO. You know what? The most recent efforts here we undertaken is trying to improve the model ENSO. We choose this one. Actually, this one is not good ENSO. We say we would like to try to say if PPE experiments can improve that kind of better ENSO in terms of the life cycle. Okay, so people complaining about the same to you about the ENSO simulation of the life cycle. We have kind of quasi-biennial cycle, and the people don't like it. But actually, out of the 10 major metrics for the ENSO simulation, according to the Cliver, so those big package, and 7 out of 10 are pretty good in SIM2. Only one stands out. That life cycle is not good. Okay, people complain about that. I talked about that before. And then we tried a lot to improve this part. Okay, try to get a better life cycle for the ENSO simulation. And so we adopted the meta-phase, the so-called UKCP 18 PPEs. There are totally 20 PPE combinations for the test. One is the control. So basically, we have one already. That control one is the standard configuration for our SIM2, the SIMIP6 delivery, actually. So we only need to do the 19. The first group we have done is only 8. Okay, so we cannot afford to run the 16 and the 19 at the same time. It will run out of our compute time really, really fast. So we done the group by group. The first group is 8, and we done 8. So we called the CJ888G 12 to 19. The numbers corresponds to the PPE numbers from the meta-phase. Okay, so we try to compare those, and so the photo number. And if you want to check the details, you can find the good description of those PPE experiments in here. I put the web link here. And we using one of the previous experiment for aspect control, and so we do this. And the second part of today's update is we do a little bit more, and we choose one from these PPEs, and we think that one is pretty good, and in terms of ENSO, of course, and other part is not bad either. So we think this pretty good choice. We do something further. And so that's basically 2 parts today's update. And one is the group of 8 PPEs, and the second part is some variants of the so-called best one we choose. And do some further tests. And yeah, as a couple model, you run, actually we care really much about the top atmosphere, the energy imbalance, okay? And in our case, the same too, if you look at our SIM6 delivery and pre-industry control, we've got, unfortunately, pretty large imbalance at the top of the atmosphere. That the TOA energy imbalance is about 0.5 watts per square meter, and it's not travel, is not good compared to the other models. Also, compared to the ESM 1.5, also our SIM5 model, actually 1.0, 1.3. But in those models, we got less than 0.1 watts per square meter. The 0.5 is way too big, okay? Which means we got kind of the model got the tendency to warm up all the time because we got extra energy into the atmosphere and then pass into the ocean. Yeah. So we're going to say all these kind of new experiments, the PP experiments, can really give us something better at the TOA and give us better energy balance there. So this is compare. The left side is the previous group of experiments using that GM parameters we just mentioned, okay? And we say this compared to the PI is not bad at all. Basically, it's around 0.4, okay? Square root. But remember, this is a present day condition. It's not a PI condition, it's a PD condition, okay? It doesn't look that bad. Compared to the right side here, the right side is the new PPE experiments. The 8 runs we showed here, including the base. This is base here, that's G, the C trip G, you see that? And now we say the best one we choose for extending got less than 0.2 compared to the control runs at 0.4, right? Which means the TOA energy imbalance improved a lot. We want this smaller sense, okay? So if we transition this into a PI condition, we expect this can give us a lot of better TOA energy balance, okay? And yes, we also care about the sea surface, right? And so a lot of things happen with the surface and so stuff like that. So we check the global mean the temperature, SST, and also the surface salinity. The salinity is a little bit tricky, as you guys know. So if you do the ocean modeling, the surface salinity is really tricky to simulate. It's hard to get it right, actually, and depends on a lot of things: precipitation, evaporation, and also runoff, everything. And we don't pay much attention to that because we check also the other things, but still, we need the ACCESS is in a reasonable range. I think this is pretty fine here in our model, even though you say this kind of a lot of variations here, also some trends, because the model has not reached kind of equilibrium in any sense, because we need to run a lot longer than this. It's a couple of 100 years, you can see this here, and it's not long enough, okay? And the SSG basically can stabilize much quicker. You can see the left side here. The good one, you see up to already 200 years simulation, this is the one. We can see that stabilize a little bit higher than the current observation. So we expect we could have 18.5 degrees or something, but this is a little bit too high, but it doesn't matter. A lot of models give a lot higher surface temperature than this, and still okay for the climate change simulation anyway. And one important thing we say, the ocean and how the ocean interior changes. Okay, so with the new force in the PP experiments, we expect something happen in the ocean because the condition from top of the atmosphere and also the surface, the energy passing and could change a lot bit. And now we say the left side, this is the global ocean mean temperature. And we have two groups here. You say the really distinction. Okay, the big distinction here. So one group, we got the ocean warming up, and one group got the ocean cooling down. And our standard configuration, that's the thin black line there. We say this one is got consistent warming up. And now the good ones, we say that trend of warming inside ocean is slowed down. This is good thing to us. We don't know, we don't want to say too big warm up in the ocean. And this one gave us that kind of thing. But this kind of cooling stuff, we don't understand why this happened yet. And because, you know, the atmosphere, the top of the TOA, we say the energy get into the system, but we say the ocean is cooling down. That's a little bit weird to us. We need to spend time if we really want to dig deep, and we need time on that. But anyway, so the longer runs here shows a better trend compared to any other runs. We say the slight warming up. And the global ocean salinity, which means the freshwater loss, again, when the salinity increase, we say, okay, the ocean lost water, fresh water. This is actually can be tuned. We can make this balance. There was kind of scheme in our model. The South Ocean, there was kind of iceberg-like melting. We can increase a little bit, which means if you increase the iceberg flux, we can get more water into the ocean. In that sense, in that case, and the ocean salinity can be dropped. Okay, we can. But anyway, so we just leave that for future. Right now, we just allow the model to develop like this. It doesn't really matter. So we model have always this kind of issue anyway. You can tune it. All right. And in the ocean interior, another part is ocean dynamics, or people pattern, not especially very important, the circulations, right? Like the overturning circulation, which, you know, plays critical part in adjust climate on the globe. So we know that, and we want the ocean simulate the reasonable strength of those kind of circulation, especially North Atlantic, deep water formation, and also Antarctic bottom water formation there. We want them at least can be compared to the other good models, including our old version of models here. We don't want to say too vague sense and associations, which means the ocean is not active, and basically that is not right. So the ACC, Antarctic circumpolar currents, and which is really important index of ocean dynamics, the circulation around the Antarctic, that circulation. The observation value there is about 173 sphere drop, around plus minus 11 sphere drops. That's fine. Okay, our model gives the original ones, and here the same black ones here shows about 119.95. It's a little bit too strong compared to the observation. And the so-called good ones now we test here also give that it's about 195. Okay, it's a little bit strong compared to observation. Only one of our other ones here, the PPE ones here, gave a really reduced from, you know, the large ones to, which is much closer to the observation. This the red ones here say this sounds good, but unfortunately this one gives some the answer is just not that correct. Okay, so as we just mentioned, the focus of us is trying to improve the answer. If the answer is not good, the other part improvement is not significant to us. So, right. The ABWF and then talk about the formation here. And all the models, global models show reasonable overturning strength here is about over 10 for drop. Okay, so if down to 10, down to 5 or 6, the probably is not that good. In our case here, all the PPE gave kind of acceptable range for this overturning. And with the so-called the best one, the G17, is around 12, right? This is pretty good. Okay, this is really equivalent or very close to our standard configuration. This one is also good. The other ones, some drop a little bit, and but still a little stronger than our ESM 1.5 case. Our ESM 1.5 case, we have about 6 to 5 spur drop. That's a little too weak, okay, for the ABBWF. And for the North Atlantic deep water formation, and we expect we keep the level is about 20 spur drops here. Now is in the every runs looks good. Okay, so it's really good. It's the other model in the other group in the world, and they probably can give from 15 to 30, that big range. If it's 20, that's really close to so-called observation. So this is good. It doesn't do any damage, you know. So this PP experiment is still good. And we check the surface temperature. SST compared to the observation, some modern time, like, you know, the current situation also. So around to the end of last century, so 30-year mean compared to that. And all the 8 PP experiments, we say the number here, G12 to G15, that's 4, this one. This is the control run. Left side, the standalone panel, this is the control runs compared to the observation. So our model always have issues around Antarctic. As you say, the SST is way too warm compared to the observation. And the other part is like this is the tropical here. You can see a lot of big warming over there. This is not good. And this is not along our model's issues. This is our model similar issues, we can say. Some have improvement recently. We haven't cut that up yet. We need to do some work later. So we got some idea to improve that. And but not in this version of the model, but we can definitely do something later. Anyway, so this 4 out of the 6, that's the 8, okay, the half of the PPE runs. Compare to observation. You can compare against the left panel here, this one. If say anything changed or anything improvement, unfortunately, if you need to look really carefully to say which part is better, which part is getting worse, okay, now. But generally, it's still not significant if you talk about any improvement over the surface, you know, so the SST pretty much, you know, so like, I really like, even you say the big difference in the patterns, but if you check the significance, it's just not really that important to me. The other 4 members here. Yeah, if you pay attention to the South Ocean, some of these experiments says, okay, this is pretty similar to control, like the 18th and the 19th, and a little bit improve over the South Ocean, which means we probably can have better simulation of the sea ice. One of the shortcomings of the CM2 models, we have really little sea ice around Antarctica, especially in summer. If we cannot improve the SST around Antarctica, which means we cannot produce reasonable sea ice simulation. And that's another part, as I just mentioned, we need to try hard to improve the South Ocean SST, right? Anyway, so this comparison gives the idea. So this PP doesn't really improve the South Ocean SST simulation. But it doesn't degrade the simulation either, so that's okay. We can work on that a little bit later. And this is X10, so we probably skip this, but as we just mentioned, the SAT is not good. We don't expect the science is good either. And we come back to the major conclusion here. And so how the ENSO behaviors in the model. Now the 8 PP experiments compared to the control, and any improvement we say from these experiments. Yes, and on the right side, okay, the right side panel here, you can see this is kind of previous group of experiments we do that GM tuning in the ocean. So for those 8 experiments, we don't see any good ENSO. And especially one stands out is really bad, and so which is G17. I'm not G17, it's AAG. Okay, this one showed here. and it's about 2 years, the life cycle of the NSO, but the variability pretty strong. Okay. You know what? For the PP experiment, I just choose this one as the base. Okay, even though the NSO is bad compared to the other ones, and why? For what is logic here? And initially it's kind of a mistake, but it turns out it's a pretty good choice, and because the other parts are really good compared to other ones. But NSO here is really bad. But if the PP forcing applied to in our carbon model, NEC can be improved from this bad behavior here. Okay, now we say the left side, we turn to the left side here, left panel. There is an arrow point to this the pink curve here, that pink curve. Okay, this is kind of power spectral. The axis is kind of a frequency of the NSO occurrence. Okay, so the 0.4, which means about 2.5 years a life cycle for the NSO, which means the smaller number of here, the longer period of the NSO life cycle. We want the peak is the left side here, because observation is about 3 to 7 years. Okay, it's especially the 4 to 5 year peak for the observation. So our model, the most of the case is peaked at about 2 years. This is not 2 years. I mean, it is right side of the 0.4 here. Okay, the 0.4 means 2.5. Okay, and now if you check this the G17 here, G17 gave us is about more than 3 years. That's from the 2 years to 3 years, it's more than over 3 years. This is a big improvement. Okay, and if you check the other case, from G12 to G19, they don't give any. It's some improve a little bit, but most of them are not really good in terms of the simulation. So the G17 is pretty good now, and a big improvement over the NSO life cycle. So we like that. That's why we kind of trying to extend, stop all other ones and keep this one going a little bit. And it's only 100-year results from this slide here. Okay, we want to extend for another 100 years to say if anything changed from this good performance here. And yeah, now we extend this G17 to another 100 years. And at the same time, we start from year 100, the end of 100 year of G17, to use different parameter for the GM in the ocean to say if this kind of cooling in the ocean can give anything significance or better in the ocean, especially the ENSO. If ENSO still be same way or differently. Okay, so this slide shows the TOA and energy balance. We don't see any significant change. Okay, with extension 100, is still stabilized around 0.2 watts per square meter. That is pretty good. We like that stabilization. And the other part, SST, SSS, and you can, yes, the SSS, the SST, we can say the last 100 years, it also stabilized, but yeah, warmer than observation and our really control runs here. And the ocean, yeah, unfortunately, we say these two extensions with different ocean parameters. We say the ocean's cooling down. Actually, we saw before, if you check, we didn't show here, but we previous group one with the GM tuning, we see these two parameter change can cause some, this is the ocean cooling down. This is our D and E case and cooling down. And it's not what we really like, but this is the G17 here. The G17, the red line here. Red line is yeah, keep warming, but it really much reduced rate compared to the original so-called standoff setup. Okay, this is pretty good. It's fine. The ocean salinity indication of the freshwater loss from an ocean or gain from an ocean. Yeah, this is if go up, the water loss, and going down is water gain. So we can tune this, as I mentioned before. We can make the little balance close to zero. Okay, close to here. It's okay. So it's not big deal. Oh yes, the ACC and the ABWF and GWF.
Dave, I'm really sorry to interrupt you. I just how much longer do you have? Just to know, because we're going way out of schedule at this point. So it's very interesting. Just want to figure out where are we going? How much longer do you have? You think you can wrap up?
3 minutes.
Okay, thank you. Great.
Yeah. Yes, this update contains a little bit too much stuff. Okay, so that's why it takes time. Thank you.
Sorry, I didn't want to interrupt right away. It's just that we also have David giving a talk, and
yeah.
just a quick update on the it's really interesting. But
okay, so that's for this extension, 100 years, and the two variants gives a little bit too big drop in the ACC. We probably don't like that, even though it's stabilized a little bit. And okay, come back to the ENSO. The ENSO, we show the different parents and different lengths of a parent, 50 years, 100 years, 80 years, and the good ones, the G17. We go to the final ones here. Okay, this is the last 100 years, which means we have two peaks here. One peak is 5 years, one peak is 3 years, which is good to us. Okay, so we like 5 years. That's 5 years, and is what we say from observation. And if we keep this tendency in our model, the G17 is a really good one in terms of initial simulation. All right. And the other sense is a kind of comparison between the different runs, and only this one stands out really good. And there's no really conclusion here, because we still need to run a model longer, and also we need to finish the other runs for the PPE. We've only done 8 runs here, 11 remaining. We want to do the similar parents simulation, probably 200 years, 100 to 200 years. And for the really sensible evaluation. This is the last slide for me, and I need to report to everybody here. So there's a most recent progress in the ACCESS-NRI development. And we started working on the high resolution SAM2, and is kind of N216 plus Quirky Ocean. This is what we expect, we look forward to work on, and for a long time. Just recently, Martin helped us to configure, the cable based on the new ocean Nancy mask, and then we can work on set up the suites for the high resolution SAM2. So it's underway, and we'll probably should start really soon when we have time and or the computer resource. So that, okay, that's what for my talk today. Thank you.
Thanks a lot, Dave. That was quite interesting.